Okay, let's dive right into this explainer. Today, we're doing a full autopsy, both technical and cultural, on the ultimate cascading failure of the world's largest interconnected machine. We are talking about the 2003 Northeast blackout. And, it's honestly a wild story about how a few localized, seemingly minor glitches, literally just 3 trees and a single software bug, managed to completely paralyze an entire continent. To really grasp the gravity of this, we have to talk scale. 50 million people. Imagine that. On August 14th, 2003, what started off as a completely ordinary, maybe slightly warm summer afternoon, suddenly plunged 50 million people across the northeastern US and Canada into total absolute darkness. I mean, water systems lost pressure, cell service just died, and traffic lights everywhere simply went out. And to put the stakes into perspective, the economic impact of this single afternoon was north of $10 billion. $10 billion! Not to mention, it's estimated to have contributed to nearly 100 deaths. So how on earth does an outage of this sheer magnitude actually happen? Well, massive catastrophes like this, they don't happen in a vacuum. To understand how the grid practically ripped itself apart, we need to rewind the clock and look at how the whole thing started unraveling long before the lights actually flickered out.
Let's start from the beginning. Section 1, Flying Blind into Disaster.
Earlier that day, the Midwest Independent System Operator, or MISO, was looking at their daily forecasts. They knew it was a hot day, and they knew a couple of generators were down, but initially, they thought everything was perfectly in the green. They were relying heavily on this absolutely crucial tool called a state estimator. Grid coordinators are constantly slammed with massive amounts of raw, sometimes spotty data. So the state estimator takes all these real-time measurements and calculates the exact current state of the grid. That data then feeds into a contingency analysis tool. Think of it as a program running constant what-if simulations 24/7 just to ensure the grid could survive if a generator suddenly dropped or a transmission line failed. But here's where the very first domino tips over. Twice that afternoon, a transmission line just outside MISO's immediate area tripped. The problem was, the state estimator didn't have an automatic data link to that specific line, so it required someone to manually punch the data in. Because of that missing data, the system threw an error. It literally could not converge on a mathematical solution. So starting right around noon, this incredibly vital predictive tool just went offline. MISO couldn't see their vulnerabilities anymore, which meant they couldn't warn the local operators about the storm that was brewing. They were flying entirely blind.
Section 2, The Reactive Power Problem.
So over in Ohio, millions of air conditioners were just blasting, running full tilt to beat the heat. And those AC units rely on induction motors, which need something called reactive power. It's a bit of a tricky concept, so think of grid power like a tall glass of beer. The liquid beer, that's your real power, the stuff doing the actual work. The reactive power is the foam. You need the foam to pour a good beer, but it takes up valuable space in the glass and the transmission lines. And because transmission lines naturally consume reactive power as it travels, you can't just easily ship it in from hundreds of miles away. FirstEnergy, the operator controlling northern Ohio, was absolutely starving for local reactive power. And to make matters worse, at least 4 of their local capacitor banks were already out of service for the day. Desperate to keep their local voltage from completely collapsing, operators at the Eastlake coal-fired plant, right on Lake Erie, started pushing their number 5 generator unit to its absolute physical limit, just trying to squeeze out every last drop of reactive power they could. But unfortunately, they pushed it a little too hard. At 1:30 p.m., the generator's own internal protection circuit said nope and tripped the whole thing offline to save itself. Now suddenly, the Cleveland area had to import massive amounts of power from the south, which put an immense physical strain on their transmission lines. Section 3. The absurdity of human factors. With the physical grid straining under the weight, we have to look at the control room. And this is where the most cynical, frankly infuriating part of this whole disaster unfolds. We're talking about a complete structural breakdown of corporate communication. Right around 2:15 p.m., FirstEnergy's alarm system, the literal system designed to loudly notify operators if equipment starts failing, got stuck in an infinite software loop. It just completely froze up. Now, the IT department noticed there were computer issues, and they quietly started troubleshooting the bug. But unbelievably, they never bothered to tell the control room operators. So the operators are basically driving down the highway at 80 miles an hour, their digital fuel gauge is stuck on full, and they are blissfully unaware that they are running on empty while the grid around them is actively self-destructing. It wasn't until much, much later that the terrifying reality actually dawned on them. As frantic reports from the outside world started trickling in by phone, an operator in the FirstEnergy control room finally uttered this incredibly chilling realization. Nothing seems to be updating on the computers. I think we've got something seriously sick. They had been completely blind, deaf, and entirely disconnected from a massive crisis unfolding on their own equipment.
Which brings us to Section 4, 3 trees, total chaos.
Okay, so remember how Cleveland was desperately importing heavy loads of power from the south? All that current causes transmission lines to heat up. Hot metal expands, and when it expands, those massive, heavy lines start to physically sag closer and closer to the ground. And here is the brutal rule of 3. At exactly 3 p.m., the Harding-Chamberlain line sagged directly into an overgrown tree limb. Short-circuited and tripped offline. The control room? No idea. Frozen screens, remember? 30 minutes later, the Hannah-Juniper line takes up the extra slack, overheats, sags into a completely different tree, and dies. Still zero alarms. 10 minutes after that, the Star South Canton line hits a third tree, trips for the third time that day, and permanently locks itself out. 3 totally ordinary trees had just quietly severed the main electrical arteries flowing into Cleveland.
And while the FirstEnergy operators were just staring at their frozen screens, the rest of the grid was literally screaming. They started fielding these frantic phone calls from nearby power plants that were suddenly experiencing massive, violent voltage spikes. In fact, a nearby nuclear power plant operator called in with this warning: "It's not looking good. We ain't going to be here much longer, and you're going to have a bigger problem." The sheer panic from the outside world was just slamming into this totally oblivious, silent control room. Section 5, Zone 3, Relays, Strike. At 4:05 p.m., with almost all the other paths totally severed, the last remaining major 345 kilovolt line, the Sammis line, overloaded and tripped. Cleveland was now 100% cut off from the south. What had been a highly localized Ohio problem was now transforming into an unstoppable continental surge. See, the grid is protected by these redundant relays that monitor for electrical faults. Zone 1 monitors locally. Zone 2 monitors slightly further out. But Zone 3 relays, they monitor from really far away. And because they're so distant, they aren't great at discriminating between a true, dangerous, localized fault and just a highly unusual but non-damaging surge of power. Acting like overzealous bouncers at a club, these Zone 3 relays saw massive power swings and just started aggressively severing line after line to protect their own equipment, which basically poured gasoline on the collapse. Section 6, Anatomy of a Blackout. With no physical way for power to reach Cleveland, Toledo, or Detroit from the south, west, or north, a massive electrical tsunami reversed direction. It flowed east into Pennsylvania, New York, and Ontario, carving this massive, destructive counterclockwise path right around Lake Erie. Once those final dominoes fell in Ohio, the terrifying speed of the final cascade took over. You guys, it took only 3 minutes for a massive swath of the entire Eastern Interconnection to rip itself apart. 3 minutes. 265 power plants tripped offline. 508 generating units shut themselves down in a total panic. This massive electrical island became completely, hopelessly unstable. The frequency collapsed, and boom, 50 million people were instantly in the dark. Now, since 2003, we've implemented a lot of upgrades and strict recommendations to fix these exact blind spots and corporate silos. But let's be real, the grid today faces entirely new pressures. We're talking extreme weather, massively increasing demands, and the rapid addition of variable generation sources like wind and solar. This massive, delicate, intricate machine requires precise, real-time balance every single second of the day. Which leaves us with a final thought I want you to consider. As we push the limits of this intensely interconnected grid today, are we just waiting for the next 3 trees to fall? Thank you so much for joining me for this explainer, and I'll just leave you to nervously eye your desk lamp right about now.